Welcome to NPTEL course on power system protection. We will start with current and voltage transformers. In this lecture, we will discuss on current transformer, the equivalent circuit of the current transformer, the burden to the current transformer calculation and the classification aspects on current transformers. To the relays, the voltage and current signals are the inputs, and these inputs, as we have already mentioned, are from sensors, current signals from current transformer, voltage signals from voltage transformers. The sole objective of these sensors or transducers are to lower the magnitude, to scale down the corresponding signals to a suitable level which is compatible to the relays, and to provide galvanic isolation, electric isolation between the power network which is of very high voltage and the relays and the other connected instruments in the system. So, we will see that earlier in all our discussions on relays, you assume that the sensors provide the signals of the systems perfectly, and based on that considerations we see that current transformers secondary windings are rated 5 ampere or 1 ampere. Different countries use, you can say that different perspective, different system requirement may be different. Also an agency may be using in general either 1 ampere or 5 ampere. Voltage transformer, some country use 110 volt, some 120 volt phase to phase voltage, or in terms of phase to neutral it is 63.5 or 69.3 volt respectively. The point here is that this higher voltage of 110 is not compatible to numerical relay, because we are confined to low voltage like 5 volt or 10 volt. So, the practice of these CT and VTs are pretty old, and they were being used when electromechanical relays are there in the high voltage system also. So, to have a retrofitting perspective, the corresponding CTs and the VTs are still continuing. So, in that respect the numerical relay may be using subsequent scaling down the signals incompatible to its own internal arrangement. Furthermore, we know that the system, like during fault, see very large amount of current. So, this current has to be scaled down by the CTs. So, therefore, the CT primary will see particularly during fault very large current. That means that the corresponding current may be as high as 50 times of the rated current. So, the corresponding CT has to manage, you can say that such a large value without any possible damage to it, and that may be for few seconds also, because the fault may persist for that kind of period. On the other hand, system voltage may be sometimes higher, different dynamic condition in the systems, and therefore, you can say that the corresponding voltage sensors VT typically you can say that having 20% above the normal value it should be able to withstand for a very long period of time. These sensors, current transformer, voltage transformer, subsequently discuss also capacitor coupling voltage transformer or simplex capacitor voltage transformer. They are required to scale down the voltage to a lower level. Now, point is a voltage transformer and the current transformer in general is associated with a magnetic circuit. So, that the galvanic isolation is being provided. Any magnetic circuit, if it goes to the saturation, then the corresponding in the transformer we know, then the corresponding current, or you can say that the corresponding current ratio or the corresponding terminal voltage, that becomes, you can say that, a different one. In that perspective, therefore, the during like for a current transformer, the current signal may be very large at times, and if it reaches to, you can say that, the saturation region of the current transformer, then the information on the primary side, which will be conveyed to the relay using the secondary, you can say that, of the current transformer, may not be the correct, you can say that, corresponding correct value of the primary. That puts challenges, and that is the reason you can say that we have this, you can say that, lecture on current transformers and voltage transformer. We will continue with the current transformer first, and then you can say that in subsequent lectures we will see the voltage aspects. Coming to the current transformer, simply if this is the conductor in the high voltage system, then we have a core and we have a winding. So, this is the secondary winding and this is the your primary of the current transformer. So, you see here that essentially require large number of turns in the secondary. The reason behind that the current has to be reduced. So, therefore, you can say that the number of turns will be accordingly should be as many. Now, there is another type of current transformer we will see in industry. This is called flux sum intensity. So, what happens that in the gap of the corresponding core, a toroid or so as it seems, then all the three conductors go through with proper insulation, and because the this area available is smaller. So, that is why this is more suitable for only for low voltage system, and this you can say that is the corresponding number of turns for the secondary, and then we have you can say that the corresponding connection to the relay, and so, and this relay you can say that represented by an impedance Z B, including the corresponding connecting wires and so. In this case, the corresponding summing city, so all the currents I A, I B, I C will be added, which nothing but gives us the 3 I 0 or the corresponding residual current and so. In this case, if you see from this to this, the difference also is that because it will be all the currents will be added. So, therefore, the CT ratio is independent of the load current. Agree? So, individual load current all three will be added, and that corresponds to consider 3 I 0. So, normally if it is balanced systems, that becomes 0, and during fault also you can say that only that by unbalanced amount of zero sequence current will be sensed by the consider the secondary. So, therefore, it is independent of CT ratio, is independent of, you can say that the CT ratio independent of the load current. Whereas, here if you think about the consider the corresponding CT, then the individual phase current is associated in this arrangement, and that is why it is associated with also load current perspective while thinking of the number of turns. Note that such current transformers which are being used in the industry are magnetically coupled, that we have already mentioned. So, that is why I need a core, and they are having multi winding transformers. Okay? There are multiple windings in this system. A high voltage current transformer may contain also several cores, not single, they can have multiple cores, and each with a secondary winding individually. So that you can say that each you can say that corresponding winding can be used for protection, can be used also control and also metering. Individual winding can be used for different applications. For example, in a substation in Indian grid, it is found that you can say there are 5 core you can say that cities. So, one core is connected to the distance and differential relay, core 2 can say that having the corresponding winding is connected to the further distance and differential, core 3 is connected to metering, core 4 is connected to the bus bar differential and core 5 is connected to the bus bar differential perspective. So, what I mean that all you can say that all the cores and the associated winding are enclosed in one you can say that as a one unit, and that is what you can say that we talk about multi winding and also you can say that multi core cities. Current transformer ratio that I 1 is to I 2 and 1 is to n, because number of turns you can say that in the secondary will be higher. So, IEEE standard says you can say that the 600 is to 5 you can say that multi ratio current transformer. Now, it is multi ratio. So, what is being done they can say that from the 600 is to 5 let us say the corresponding winding. So, this is 1 is to 120. So, that means that the number of turns available in the secondary, from the different number of turns you can have a tappings, and then accordingly you can say that the ratio will be also different. So, that you can say that tappings and the corresponding ratio can be considered used for different current transformer transformation. Like for this one 600 is to 5, the manufacturer can should provide you can say as per this standard 50 is to 5, 100 is to 5, and like this you can say that 300 is to 5 and continuing, and the 600 is to 5. So, if we say from this 600 is to 5 CT, so this you can say that gives you 1 is to 120 the turns ratio, then 50 is to 5 it is 1 is to 10 turn ratio. So, that you can say that from the same winding you can have different tappings to have you can say that different current ratio availability from the systems. Other available cities you can say that similar you can say that things are available as per the standard 1200 is to 5, 2000 is to 5, 3000 is to 5 and like that 5000 is to 5 and so. On the selection of the cities, the city ratios are selected to meet maximum load current requirement, because this is a continuous rating, faults are rare in the system. Primary of the city should meet the maximum load current, that is what we saw this also in the distribution system overcurrent in the overcurrent design also. City ratio should be large enough so that city secondary does not exceed 20 times rated current under the maximum symmetrical primary fault current. So, we say that here city ratio should be large enough so that the city secondary does not exceed 20 times. It means that for fault conditions the city secondary should not you can say that go for beyond 20 times over its rating of this one. That is what you can say that a guiding factor for this. Accordingly, you can say that the city ratio should be selected for a given system. On furthering the current transfer ratio, we say you can say that here one example. Let us say you can say that a city lead runs 200 meter in a switch yard, EHV substation, high voltage substation. So, that resistance of you can say that the wire, the city lead can be as high as you can say that around 300 ohm, 3 ohm. Now, let us have simple calculations in terms of the burden. The city burden we define in terms of the burden as if this ZB considered is talk about the burden perspective. So, then which is the corresponding wire impedance in the secondary and also the corresponding relay or any other you can say that the elements connected to the secondary of the city. So, that impedance if we say ZB, then the burden to the consider transformer is I square ZB. So, that is the load you can say that connected in the secondary load to the secondary winding. So, that is why I can say called city burden volt ampere equals to secondary current square into the impedance equivalent impedance of the connecting lead and you can say that the elements connected to the secondary winding. Let us consider a 5 ampere CT and we have 3 ohm lead as in this system. So, that leads to a Bourdon amount of I square into the I square into 3. So, this is continuous rating 5 ampere, 5 square is 25 into 3 75 volt ampere. Then we have a relay burden. Let us say electromagnetic relay has a typical burden of 10 volt ampere and if you have numerical relay it may be less than much lesser than 1 volt ampere also. So, considering the higher side 75 plus this 10 volt gives us 85 volt ampere, but this 85 volt ampere for the CT seems to be very high and accordingly you can say that because volt ampere is more. So, the corresponding say that the conductor size will also you can say that will be thicker and which will be pretty expensive. If you go to the 1 ampere CT, the corresponding current rating is small. So, I square into these 3, 1 square into this 3 becomes 3 volt ampere plus the burden of the electromagnetic relay assuming 10, 10 plus 3 becomes 13. So, as compared to 85 this becomes 13. So, we see here that the burden is much smaller. So, the expected you can say that the economic aspects should be smaller. Only you can say that additional thing here is that the number of turns in case of 1 ampere will be more you can say that as compared to the 5 ampere CT. So, we can have a meaningful comparison of these corresponding size, weight and cost between these two and then someone will prefer this, but those are you can say that again constants in terms of the utility what they have the common practice and so. So, this is on the basis of you can say that preference technical preference between 5 ampere versus 1 ampere kind of thing. Now, in case of very high you can say that current rating in the high voltage system also 2000 ampere and so you can say that the secondary current can be used to limit the number of secondary turns. Sometimes you can say that we may prefer 5 ampere over 1 ampere because the number of turns and sometimes you can say that you can exceptional case also you can go for 20 ampere CT where you can say that you can again you can say use another level of transformation with an interposing CT that of 20:1 also. So, this is about something on the current transformer ratio selection. One thing that we see that for a 3 phase systems each phase you can say that current has to be tapped and that should be the input to the relay. So, the corresponding currents are being processed in the relay. Now, unless there is a proper polarity of the corresponding current, then we cannot you can say that integrate the corresponding currents properly. So, therefore, while connecting the CTs, we essentially require the corresponding polarity of the transformer. CT or VT or so you can say that any transformer has the corresponding polarity marking. So, conventionally what is being done that which gives us the corresponding direction of the winding in the core. So, we put a solid mark at the both at the high voltage and at the low voltage or in the secondary side with these starting points. So, you can say that this mark and this mark at the starting point. So, what it shows that with respect to the starting point, then if you go to the other end, then the in both the you can say that windings in the core will be wound you can say that in the same you can say that sense either clockwise or anti-clockwise. So, that you can say that this is being revealed by this marking. In some of the cases you can say that it is being marked you can say that also H1, H2 high voltage side, X1, X2 in the low voltage side also. So, also in the transformer also and this helps is you can say that that point that if the current is entering to the you can say that to the mark terminal the solid mark or the H1 and the current you can say that if it is leaving to you can say that to the mark terminal, then both the currents will be almost in phase and the corresponding voltage from the other terminal to that marked one, in this case also these two V 1 and V 2 voltage they will be also in phase. So, that gives us you can say that scope about the proper connection for the CT. If you have you can say that polarity marking and you connect you can say that in accordance with that. Now, what is the requirement of essential requirement from a good CT or from the protection perspective and so. As we know that the CT should you can say that give us the corresponding current in the secondary. Which current? It will be a scaled down current, but we know you can say that all our analysis is based on you can say that on the primary side, the system side current and so. In a numerical relay, if the corresponding CT ratio is being multiplied to the secondary current, then the relay can know you can say that the corresponding primary current. That is what we have learned. Now, if that is so, you can say that all the calculations can be done in terms of the primary level or the system level currents, for which we have already analyzed in terms of that. Now, this CT which we are discussing now is a magnetic coupling, it has a core, and we know any transformer core may there is a chance of saturation at times. If that happens to be there, then the nonlinearity between B and H, IM and the induced EMF may be lost beyond the saturation, and therefore, you can say that the proportionality may not be there. In that case, then there is challenge and so, and that is what we say. Now, what is the expectation of from a CT? That always the corresponding secondary current should provide the proportionate value of the primary current. So, the current transformer output signal which is the secondary current is input to the relay, it should be accurate reproduction of the corresponding primary current, accurate reproduction of the primary current. Current transformer used for relaying are designed to have small errors during fault, and while their performance during normal steady state currents may be compromised to certain accuracy. We require you can say that their correct reproduction particularly during fault condition. Now, if you see this you can say that plot this situation, this is pre-fault current, fault inception point, and the current goes very high value primary current with a some decaying DC and so. Now, the secondary current is scaled down, this is depending upon the ratio, and then this is the secondary current for this case. So, what happens you can say that here if you see if you plot the both you can say that in terms of scaling I am say that referring the corresponding primary current to the secondary current, then only you can plot, otherwise this is a very large value going beyond 5000, this is only within 100 ampere or so. So, if we convert the corresponding primary current to the secondary by dividing the primary current to the suitable the corresponding turns ratio, and you plot you can say that. So, you see here you can say that secondary current is red one and the primary current is blue one, then we say that this is exactly matching with this one. So, it means that if this secondary current is fully available to the relay will multiply simply the CT ratio and can get you can say that the correct value of the primary, and that is where the reproduction is perfect. But this is ideal condition, if the corresponding current becomes very large and decaying DC will be there, and so there is a possibility of saturation of the core, and this you can say that reproduction of the secondary may not be possible always. We will see that in the subsequent lecture. Now, we will first analyze the steady state performance of the CT, and then we will go to the transient performance. So, this is about first we will draw the equivalent circuit diagram of this transformer CT, and from that you can say we will try to analyze how will it perform during steady state. So, this is primary side and this is the secondary side. In the secondary side we have the Bourdon, and this Bourdon resistance, the Bourdon impedance or resistance is as already mentioned, is the impedance of all the relay meters connected with the secondary. If plus the corresponding lead, you can say that impedance, and that you can say is the total burden to the CT. The CT has certain leakage reactance. So, the secondary leakage reactance is ZX2 and primary reactance is ZX1 prime. We have swiftly taken. Magnetizing impedance is Zm dash, and then you can say that these are the windings, you can say that primary may be typically 1 turn, or you can say secondary may be number of turns 1:n. So, with this you can say that the corresponding current input to this, you can say that primary, which is the conductor of the system conductor, transmission line conductor, transformer conductor also. In that the corresponding current flows. Note one point here, for the CT, the current which is being input to consider to this primary is the conductor current of the system, and that is you can say that you can say that does not depend upon the corresponding CT burden also, that is independent of this corresponding CT. So, that depends upon the load and the system operating condition. So, therefore, this current you can say that here the corresponding current injected to the CT depends upon the system condition. So, this is therefore, for this you can say that transformer the corresponding input signal becomes a current source kind of thing. Right? So, the equivalent becomes a current source. Now, with this you can say that if you go to you can say that the transformation of this one referring everything to the secondary, because our measurement side is on secondary. So, we say consider the equivalent becomes Zm, I1, Zx2, I2 and Zb, everything referred to the primary. We neglect here you can say that the Zx1 here, Zx1 prime here, and we do not include here, because as I mentioned you can say that the current you can say that is independent of the CT parameters, and so that depends on the system condition. So, that does not you can say that create any problem, that does not you can say that have any influence on the I1 perspective. And our objective here is that how the corresponding I2 can say that faithfully can say that reproduces the corresponding I1. Here this I1 is already referred to the secondary side. Now, here you can say that this I1 equals to I1 dash upon n is the number of turns in the secondary, Zm equals to n square Zm dash, and so. So, we got to consider in terms of this. So, we got this equivalent of this primary and secondary into everything referred to the secondary side. Now, with this we see here you can say that the corresponding input current, that I1 which is that of the conductor current referred to the secondary, two components here, one goes to the secondary side, secondary you can say that winding perspective, and one component is the magnetizing component for the CT. Any transformer has certain magnetizing current component of current, because this is having a magnetic core. So, this I2 goes to this burden, accordingly you can say that the burden to the CT will be there. So, for this case you can say that if you see the corresponding phasor diagram. So, if you say you can say that EB as a reference. So, to this EB in terms of the in accordance with the ZB, there will be corresponding current of I2, and I2 and ZB are you can say that I2 into ZB is nothing but your EB. So, and then to this I2 we will add IM, the magnetizing current lagging almost 90 degree, because of this Zm is very close, having a very large angle close to 90 degree. So, this IM is added which is having this, and that gives us you can say as I1 perspective the input current to the CT and therefore to the secondary. Now, once you get this this I1, now you see from this EB you add the Zx2, the drop is here. So, EB plus you can say that I2 Zx2 that gives us this EM, and from EM you can find out this IM, EM upon you can say that Zm gives you this IM, and once you IM you can say that. So, I2 plus you can say that IM gives you this I1. So, we got you can say that all you can say that currents and voltages from the parameters of the CT. So, that way I can in terms of equation also you can express EM equals to EB plus Zx2 I2, IM equals to M by Zm. So, I1 plus I2 plus IM gives you this I1, and then we define now two error terms. The first one you can say that we say per unit current transformer error. So, that becomes the error becomes what? Now, this you know here now the I1 is referred to the secondary. So, that you can say that I1 that corresponds to the primary current. Now, this I 2 should be equals to I 1. See, this is what desirable, the I 2 should be equals to I 1, but that is not so here, and the due region you can say is nothing but this I m current. In an ideal case, if this Z m becomes infinity, then this I m becomes 0. So, I 2 becomes equals to I 1. So, that is what desirable, that is what we considered earlier, but now we can say it seems here that if there will be I m to magnetize the corresponding core, then depending on the I m there will be inequalities you can say in the CTs. It means that the relay which will be getting this current is I 2, not the I 1. So, that leads to an error of I 1 minus I 2, and that equals to I m. If we divide upon I 1 to normalize or to make it per unit current, so that becomes equals to epsilon, and that you can say equals to I m upon I 1. So, what is the error component here? The error is only solely responsible against that the component is nothing but the magnetizing component of current. So, that is why I m upon I 1. The error epsilon is small for larger Z b, and this error epsilon is small for larger Z b and vice versa. Theoretically, when Z b equals to the epsilon is smaller for Z b, you can say when you say is a short, agree, the I m, if say you can say that very large value of Z m, then I m is smaller, very small value of consider Z b, then what will happen that because this path will be, this path you can say that will be very low impedance path. So, therefore, you can say that this most of the currents will flow through this one. So, that we say here the epsilon error is small for smaller Z b and vice versa, and this epsilon error also you can say governed by this Z m part also. If the Z m becomes very large, you can say that will be also smaller, you can say in general. Theoretically, when Z b becomes 0 and with Z x 2 in general smaller because of the leakage impedance path, so then the epsilon tends to 0 and I 1 will be almost equals to I 2, and that is what you can say that. Note that we do not have control over much on this Z m part, but we have a control over the Z b part, which is the Bourdon impedance in the system for a given CT. The ratio correction factor is defined as R equals to 1 upon 1 minus epsilon. The epsilon we have computed is here. If you go by this, you can say that if we manage by this becomes equals to I 1 upon I 2. So, what we say that whatever I 2 the relay sees, if you multiply this R the correction factor, then you can get the corresponding correct value of I 1. Why the inaccuracy? Because of this I m. So, therefore, you require a correction factor to take into account this error, that is the epsilon, and that correction factor is R 1 upon 1 minus epsilon. So, if the relay knows, you can say the corresponding I 2, and by any means if it is known this corresponding R value, if it multiply that R value, then you consider the correct value of I 2 can be found out, which will be proportional to the I 1. Note the epsilon, you can say that the R are also the complex number, all are considered in terms of the phasor representation. But many times the epsilon r simply magnitude is also adequate to for the explanation and so. Now, let us take an example. A current transformer with a turns ratio of 600:5 turns ratio, 1:200 to consider it in number of turns, a secondary leakage impedance of 0.01 plus j 0.15 ohm and a resistive burden of 1 ohm. If magnetizing impedance is 5 plus j 17, this part, find the correction factor, means the R, capital R, compare the correction factor for an inductive burden of j 1 ohm. First, we have considered for simple burden of resistive burden of 1 ohm, and then we will go for the inductive burden of 1 ohm. So, in this case, in the equivalent circuit diagram what we have discussed earlier, that we know the different terminologies, and note that in this case generally the Z x 2 is much smaller. So, Z m value given, Z x 2 value and Z b value. So, all impedances are given to us, and what we have to do, you can say that what will the corresponding error, the correction factor error, you can say that we have to calculate. So, epsilon we will calculate and then we will go for the R value. So, for epsilon we require I m upon I 1. So, we know we can say that you have to calculate first E m, and then from the E m divided by Z m will be also the corresponding I m. So, what is E? You can say that the corresponding E m EM is nothing but I 1 into the corresponding Zm, the all impedances are given. So, I 1 and we are talking about, you can say that the I 1 into the all the equivalent impedance. So, I 1 into all the equivalent impedance Z x 2 plus Z b series in parallel with Zm. So, substituting this value, you can say that we got the consider the corresponding EM to be in terms of I 1, you can express them in terms of I 1. So, I m equals to EM upon Zm. So, we can express I m in terms of I 1 also, and then you can say that the per unit CT correction error is I m upon I 1. So, we got the I m, the corresponding epsilon to be 0.056 with an angle of minus 62.24 degree. Correction factor R equals to 1 upon 1 minus epsilon gives you 1.025 with angle 2.91. So, we multiply this part to this I 2 whatever the relay will see, then you can get the correct value of I 1. Now, for the inductive load of, you can say that 1 ohm, if you substitute the same, you can say that all the perspectives. So, EM becomes you substitute only this change value is here only. So, that becomes I 1 into this, and you got the corresponding epsilon for this case to be 0.061 with an angle of 14.93 degree. So, this both angle and magnitude change now for epsilon, and you know epsilon and R are complex number. So, R becomes equals to like this 1.062 with an angle of 0.957 degree. So, for the both the cases Z b equals to 1 ohm, Z b equals to 1, if you compare, you can say that the epsilon is higher for the inductive case, and so you can say that also the corresponding correction factor becomes higher. In general, for the resistive burden, we will have less error compared to same amount of inductive burden. So, if you know the corresponding inductive burden, you can say that what is the corresponding epsilon or error part, then if you can say that system will be connected to more resistive of the same value of the inductance, then you say that the corresponding error will be less than that. So, always you can say that you require prefer always you can say that the corresponding error to be as small as possible. Now, on class of CT as per the IEEE standard. So, CT classification we can see we are discussing on protection perspective, but CT is available are for both you can say that protection class and metering or measurement class. So, we will discuss only on the protection class perspective. The IEEE class designations of a CT it defines in terms of two integer parameters C at T, and for example, 10 C 400 or 10 T 300. So, we have a integer before this C and we have an integer after the 400, and we have an integer before the T and after you can say the T also. Now, the letter C in the class designates imply that the transformer design such that the CT performance can be calculated, C for calculated, and the T signifies some uncertainties in the transformer design, and the performance of the CT must be determined by the testing the CTs, agree, and that is I can say T for the testing and C for the calculation. So, we can calculate the corresponding performance of the CT based on for this, but for this require the data sheet provided by the manufacturer. Now, what this 10 and 400 and 10 and 300 in these two reveal? The first integer 10 here describe the upper limit on the error made by the CT when the voltage at its secondary terminal is equal to the second integer, when the voltage in the secondary terminal is in the secondary burden is such that this voltage will be 400 volt, while the current the transformer is 20 times its rated value. When this is being evaluated, the corresponding transformer you can say that current will be 20 times of the rated value. So, if it is a 5 ampere CT, so the corresponding current should be 100 ampere in the secondary, agree, that is you can say that. And what is this 10? The 10 reveals about the error you can say that made by this in terms of 10% error, percentage of this error, and this 400 reveals the corresponding voltage in the burden when you can say the corresponding current is 20 times of the rated one. So, if you see this 10 C 400 here, this corresponds to percentage error and this corresponds to the secondary voltage 20 when the corresponding current becomes 20 times of its rated value. Accuracy is specified by percentage error, and you can say that that should not you can say that exceed you can say that for that particular class as per the IEEE standard, and the ratio you can say that error is always you can say that 10 in general, but there are other standard also ISC standard and all these things. So, they have their own you can say that definitions and all these things, but there are tables also available in terms of the comparison that IEEE standard this class or this rating what is the corresponding IEC you can say that rating and so. The IEC standard burdens for the relays are 1, 2, 4, 8 ohms standard burdens, all with an impedance angle of 60 degree. However, the CT is classified by voltage across the burden, that is we say this voltage 400 volt or so. So, the corresponding voltage becomes in terms of 100, 200, 400 and 800. So, this part you can say that which we are talking about in terms of this you can say that impedances corresponds to 100, 200, 400, 800. This is what as per the IEEE standard. Now, we will go for a burden calculation example. Let us say a current transformer of 500:5 with a primary current of 6000 ampere of CT class 10C400. What should be the value of ZB? Agree? The burden impedance you can say that to maintain the corresponding CT class of this 10C400, it means that 10% of error for a 400 volt you can say that in the secondary for the when the corresponding current in the CT becomes 20 times of its rated current. So, this the CT is of 500:5 ampere CT. So, this corresponding secondary current maximum current becomes 100 I am say that 20 times means 5 into 20 is 100 ampere, and the current which we like to check you can say that which the fault will have been 6000 ampere in this case. The equivalent circuit diagram as you know here. Now, I will go for the solution. The CT secondary winding is rated at 5 ampere. So, 20 times of that you can say is 100 ampere, at which you will evaluate the corresponding error. This error you can say that as per here 10C. So, 10% maximum error the CT should have. So, this is CT you can say that this class should have an error of 10% less than 10% at a secondary current of 100 ampere for burden impedance which produces you can say 400 volt. The burden impedance is such that at that time you can say it should have 400 volt maximum or less at its secondary terminal. If it is less, it is good also. The magnitude of the managing current impedance for maximum error, because we have 400 volt. So, let us neglect the corresponding impedance leakage impedance. So, if you have 400 volt, here it is almost 400 volt, 400 divided by consider the corresponding 10% error, 10% error who creates? The IM creates. So, the corresponding IM you can say that is responsible for. So, IM the epsilon is IM upon I1. So, therefore, 400 volt divided by the corresponding 10% of 100. So, that you can say it becomes equals to 40 ohm. So, we say you can say that the 10 ampere 10% of 100 ampere is 10 ampere. So, 400 divided by 10 ampere becomes 40 ohm. For a primary current of 6000 ampere, the nominal secondary current will be 6000 divided by the turns ratio of the corresponding CT, that becomes 60 ampere. 60 ampere is the input current. So, 10% maximum current will flow, that corresponds to 6 ampere. So, at this managing current will be the corresponding maximum secondary voltage 6 ampere into the corresponding 40 you can say that is about the corresponding ohms of the Zm you can say that. So, this becomes 240 volt here, 240 volt here. So, 240 volt here divided by this impedance is divided by this current is 60 minus 6, that gives you can say that the burden impedance to be 4.44 ohm. That I mean to say that ZX2 we have neglected, and that is as usual also. So, that gives you can say that is that from this way if we calculate the burden impedance found out to be 4.44 ohm, and that is the maximum one. If the corresponding burden impedance is less than the one, then you can say that the 10% the error will be less than 10%. If it will be more than that, the error will be more than 10%. So, that will reveal that, and for that kind of CT, that how much you can say that burden impedance will be there. So, the corresponding lead and the corresponding number of relays, and so the way it should be connected such that you can say that the burden impedance does not exceed this 4.44 ohm. Another example, consider a CT with a turns ratio of 500:5 and the managing characteristics for different ratio is given below. This is the 500:5 below. It is required to calculate the current in its secondary windings, for primary current of 4000 ampere. When primary current flows 4000 ampere, what will be the corresponding secondary current, that we will like to know. So, that will reveal also you can say the corresponding error also given considering the magnetizing characteristics. If the total Bourdon impedance is 8.J3 ohm, which seems to be higher, and the secondary leakage impedance is negligible, that we generally consider, the impedance angle of the magnetizing branch is 65 degree. Impedance angle of the magnetizing branch means angle of Zm is given data is 65 degree. IEEE standard says they consider it as 60 degree, but here given 65 degree. In that scenario, what will happen to the secondary current for a given primary current of 4000 ampere? Magnetizing characteristics given is like this. Now, I will go for the solution. So, as I say, you can say that for this CT, the corresponding current being injected from the system side. So, therefore, this is a current source kind of thing, very rarely, but it happens you can say you see here this becomes a current source for the CT. So, how much current will be there if you refer everything to the secondary of the CT, 4000 ampere in the primary divided by the CT ratio, then that you can get you can say that 40 ampere secondary current. So, this 40 ampere current is being input to the can say that to the relay to the CT, and that leads to can say that in the CT secondary equivalent circuit we have seen the corresponding branch of Zm, the magnetizing current, and the Zb, the Bourdon impedance. Bourdon impedance already given here 8 plus J3, and the Zm you can say that is unknown to us here in this case. So, this 40 you can say that if we go for the Thevenin's equivalent of this one, then we will get like this, because these two components are given to us. So, we have the Thevenin's voltage of 341.76 and the corresponding series resistance of 8 plus J3. Now, this you can say there will be a Zm. So, this becomes a series path for this Thevenin's voltage. If you like to solve, you can say that the corresponding issue of how much will be the corresponding secondary current. Only given that the Zm is having a 65 degree angle. Now, this Im in that diagram if you see, that becomes equals to Thevenin's equivalent divided by this corresponding series impedance. Zm is unknown, but you can say that the angle we can is available to us. This corresponds to the corresponding angle, and then you can say that the corresponding relay Bourdon is 8 plus J3. So, this is you can say that from this you can find out E2 equals to Im into Zm. Now, what do you do with that, because the Zm is not given, you vary the Zm with different values, you can tabulate for a number of you can say that values of Zm, and then you can say that substitute this value magnitude of Zm, and then you can say that you can get the corresponding Im values here, and this E2 value here, E2 is Im into Zm. So, like this you can tabulate some of the points here I have tabulated here you can say that, and then once you have this tabulation. So, what you do that you plot you can say that the corresponding E2 versus the corresponding Im line, and that line you can say that crosses the you can say that at this point you can say that at this point to this the corresponding magnetization characteristics, and you got the value you can say that for that situation for that Bourdon the corresponding 19 you can say that 19 ampere, and then the corresponding value of you can say the secondary voltage to be 250. So, with that you can say the data you can say that what we say now we got the corresponding all perspective Im equals to 19 ampere, E2 equals to 250 volt. So, I1 equals to I1 injected current is 40 ampere. So, now you like to find out this I2. So, given that you can say the system parameters and all these things. So, from that Im equals to this means you can find out the Zm value, and then you can say that Im upon you can say that the corresponding I1 it becomes equal to epsilon equal to this, the corresponding R factor also becomes this, and you can say that we say you can say that what it reveals that the CT is in a severe saturation current, because the epsilon value is very large here you see here as compared to the earlier discussions we made, and that you can say that why the saturation we expect you can say that because it goes to consider to the saturation in a region in the BH curve, and that is the region the corresponding error becomes this. What the error reveals? That the corresponding I2 which is being seen by the corresponding relay is having a much you can say that smaller value because of this significant Im as compared to the injected current I1. So, the Bourdon should be reduced, the Bourdon it seems to be very high. So, in overall our remarks you can say that is that a CT with a standard Bourdon having a impedance angle of 60 degree produces less than 10% error at 20 times current, and a resistive Bourdon of the same value will produce less than 5% error. This is a general remark when that calculation is observed that resistive Bourdon will having less error as compared to the same value of you can say that inductive Bourdon. City selection in terms of IEEE standard suggests that cities for relaying be applied such that the maximum symmetrical fault current does not exceed 20 times the city current rating, and that the burn-on voltage does not exceed the accuracy class voltage of the city. So, preference should be that the city current does not exceed, you can say that 20 times of the city rating, and the burn-on you can say that should be such that you can say that the corresponding class being satisfied. When city saturates, the managing current increases substantially, resulting more error that we see. So, the burn-on should be incompatible to the requirement for the accuracy class of the city. So, this is all on city, you can say that steady state behavior. Thank you.